How do you do, ladies and gentlemen, teachers, boys and girls? I'm Julius Sumner Miller, and physics is my business. And we come once more to what I have entitled Further Adventures in Electromagnetism. The subject is filled with drama, quite stirring to contemplate. Consider the following. Here is a horseshoe magnet, very, very strong. Indeed, strange properties. It is called an alnico magnet. And imagine this: nickel, highly magnetic; cobalt, highly magnetic; aluminum, or for the Britishers and the Australians, aluminium, very feebly magnetic, if indeed at all. And yet, when put together in proper parts, gives us a fantastically strong magnet. So here is an alnico magnet. I'm going to show you how strong it is. There is a keeper, a bar to put across its terminals. Watch. Oh, it's a very strong magnet. Now, I am going to put a wire, a limp, feeble wire, in between the poles. Very loose wire. And I'm going to give rise to a current in this wire by connecting to a storage battery. Watch the wire. Watch it. Oh, it jumped. It jumped. There it is. I want to do it again. There it is. Why? Well, the current-bearing conductor gave rise to a magnetic field which interacted with the magnetic field there, and the forces were enormously stout. Consider this more enchanting. I have a typewriter roller. You know, the roller on your typewriter. And I have wound it with some turns of wire. And the ends of this winding I'm going to connect to 110 volts AC in this room, like in your home. This means that the coil is energized with an alternating current, which grows and decays and grows and decays. Therefore, we have a change in the magnetic flux, and therefore a changing magnetic field here around this coil. I'm going to show you what it can do. Here is a little coil of wire, few turns, to the ends of which I have an automobile headlamp fixed. I am going to close the circuit, energize this coil, and bring this lamp down. Watch it. Fantastic. No physical connections whatsoever. None whatsoever. Only electromagnetic. Consider this. A copper ring. Solid, heavy, large cross-section, small ohmic resistance. I'm going to rest this ring on my hand, so close the circuit. The current in this primary coil gives rise by induction to a current in this, and they both give rise to magnetic fields which are repulsive in nature. Watch this now. Watch it. There it is. It jumped up. Indeed, let me take two of them. Two of them are certainly heavier than one. Watch it. We'll see an astonishing thing. The jump is even higher. There it is. And if indeed I took a whole string of them, 5 or 6, you see they constitute a single conductor of larger cross-section and hence of smaller ohmic resistance. Watch this now. Watch this. This is terrific. There it is. Now, here I have a coil of wire, protected a little with adhesive tape. I'm going to put this coil of wire near this coil, but no physical connections there. And this secondary coil is connected to an ordinary, what is that, a 40-watt lamp or some such. I'm going to energize the primary. Let's see what happens to the lamp. Very feebly lighted, very feebly. Why? Well, this is an air core. Very low permeability. The induction is very low. So what am I going to do? I am going to put an iron rod in the core of this secondary and watch the lamp. Now, watch it. Watch it. Somebody says, what's that hum? Well, 60-cycle hum about which I won't say anything here. But do you notice how strong, how much the induction is aided, enhanced, abetted, favored by making this core highly permeable with soft iron? Here's something that I could do. We'll imagine this as a virtual experiment. Here is a hollow tube. Oh, wait a minute, hollow tube. I think that language is redundant. Just a tube would be good enough. Copper, closed, with a little side arm and a tiny, tiny hole. What would I do? I would fill this tube with water. I would then hold it with a pair of pliers, bring it down over the induction coil, and nearly instantly, the water in here boils. Why? Well, the induction heating is phenomenally rapid, and the water is brought to a boil, and I have a question. There is only one entrance to this tube, one tiny little hole. Question, how can I get the water into that tube? How? That's a good one for you to contemplate. So then, for electromagnetic induction and the business of my jumping rings. But before I finish, the hole in this typewriter roller I have filled with strands of baling wire from bales of hay, very soft iron wire. I say that when I energize this coil, this becomes an electromagnet. Proof. I have here an iron bar. I'm going to hold that about an inch above, close the circuit. Watch. Watch. Going to hold it. Notice I can't hold it. Two men couldn't hold it. Why? Very strongly magnetized. Let's look further. Electromagnetic induction. This one is filled with drama, enchantment. Here is an aluminum disc. Aluminum. Remember my commentary. Aluminum is not magnetic. Correction. It is magnetic because all stuff is magnetic to more or less degree, but it is highly, highly non-magnetic, or feebly magnetic. I'll show you that it is feebly magnetic. There ain't no stuff there. Now I'm going to mount this disc on a vertical pin so it can spin on a vertical axis horizontally. But I'm going to put it at rest. Here I'm going to take the magnet hanging on a piece of clothesline, and I'm going to twist up the magnet so, storing some twist energy, as I am given to say, in this string, so that the magnet now unwinds of its own accord. Now I'm going to hold this centrally over that disc which is at rest, and you will witness an extraordinary thing. Watch it. Watch it. That disc is turning. That disc is turning. Now somebody says, Professor, that disc is turning because of the viscous friction of the air. It drags it along. No, 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 no. No dragging along. Here's what's happening. The rotating magnet gives rise to induction in the plate. In the plate, there arises an electric current. The electric current in the plate gives rise to a magnetic field, which interacts with this magnetic field. And this that I have shown you is the classical demonstration done by Jean-Dominique Francois Arago, A-R-A-G-O, a wonderful Frenchman, and so we call it Arago's disc. Regarding Arago, he made a commentary concerning Gauss, the great German mathematician. What did he say of Gauss? Carl Friedrich Gauss. Gauss. He calculates with the ease as eagles do fly. He calculates with the ease as eagles do fly. That was Gauss. So, electromagnetic induction. Here is another one of like complexion. Here is an aluminum disc, and as you would expect, if I showed this in Australia or the UK, I'd have to say aluminium. Here is an aluminium disc. It's mounted on a vertical shaft, and it's free to spin horizontally. I'm going to spin it, and we'll get a feeling for its spin life. How long is it going to spin? Watch it. quite some time. Now, here is a strong magnet, powerful magnet. I'm going to advance the magnet so as to embrace the disc in the magnetic field. Here we have a moving conductor in a magnetic field. A current is induced in the conductor. That current gives rise to a magnetic field which interferes or interacts with the magnetic field here. Watch it. Watch it now. A magnetic break. And the principle that we have here invoked of the disk being brought to rest by the interaction of magnetic fields is known as Lenz's law, L-E-N-Z, a Russian who gave us this matter. So, mark you, on occasion I have taken a moment to name the men associated with our affairs. And in nearly every instance, I have tried to point out the national origin. Michael Faraday, an Englishman. Gauss, a German. Lenz, a Russian. Who else? Isaac Newton, an Englishman. Einstein, a Jew. And so, Ohm, a German. Ørsted, a Dane. What I'm trying to say is, it is very essential to pay proper tribute to the national origin of these men, for no single peoples have any special claim to intellectual competence. A magnetic break. Talking about magnetism, let's go back to an old-fashioned matter. Here is one of those strong Alnico magnets, and I'm going to toss some nails into the field associated with these two poles. Watch it. Watch it. Look at that. Look at that. And the reason I do this is to point out the following. Let us look at a horseshoe magnet. Here is a horseshoe magnet. If this is of north polarity and this of south polarity, the field across here is very, very strong. And I am reminded of an experiment that Michael Faraday did for the children in the Royal Society. What did he do? He threw some iron filings at random, and it made such an arch, and he described it as a little tunnel through which a little mouse could go. You see the humanism that filled Michael Faraday's spirit. He thought of a little mouse going through this little tunnel. And so, where are we? Electromagnetic phenomena, first observed by Ørsted in 1820, when he discovered that a current-bearing conductor gives rise to a magnetic field, and then 11 years later, advanced so profoundly by Michael Faraday with his discovery of electromagnetic induction, which, I always say, lighted the world. And I thank you for listening.